Hey guys, one more section left in chapter 4, and this section is on rational functions. And the word rational, if you look at it, has the word ratio in it, and we know that a ratio is a fraction. We can also take this to just the basic definition of rational numbers, signified by the symbol q. Rational numbers are fractions that can be made from integers that terminate, such as 1/2. That'll terminate because 0 0.5, there's nothing else after the 5, terminates, or repeats. And something that repeats, it has a number that just continues to cycle through, such as 6 divided by 11, which is simply 0.545454. And we write it as 0.54 with a line over it. So rational functions are fraction. They're quotient. And for what we're looking at, it is considered to be a quotient of polynomials, meaning that I have a polynomial in the numerator and the polynomial in the denominator. Remember, polynomials can be made up of monomials and binomials and trinomials, so they do not have to be some massive, eighth degree. We can simply have to the first degree. All right. Also remember, numerator is the top portion, denominator is the bottom portion. The line that separates the numerator and the denominator is called the vinculum. This means to divide. It's another division symbol. So, with our rational functions, the main takeaway from this section is being able to understand that there are some places where the rational function just will not be graphed. And we'll get into that and be able to look at it and explore it. But the graph will never touch certain spots, or what you could even say is like a line through the graph. It'll never touch that line. This can create a break in the domain, which is why we don't consider rational functions to be polynomials, because our polynomials have a domain of all real numbers, negative infinity to positive infinity. A place where the graph cannot touch the line, it, it will either be labeled something as simple as x equals c, where c is a number, so just a basic vertical line that intersects the x-axis at c, whatever number that is, or a horizontal line such as y equals c, just whatever number c is, and that would be a horizontal line. This line is what we know as an asymptote. Now we can also have some that we call slanted, to where they're not just perpendicular to one another, such as vertical and horizontal. We can have it to where there has a slant, and we call that the oblique, which leads us into the three types. The three types of asymptotes that we have are vertical, horizontal, and oblique, and we will talk about all three and what this means. Basically, this will be a vertical line, this will be a horizontal line determined by the leading terms coefficients. So the a represents the one in the numerator and b represents the one in the denominator. And then we have the oblique, in which we'll find an actual line to determine what is the oblique asymptote. Key takeaway, asymptotes are not a part of the graph. Think of them more like a boundary or a guide for the graph. So let us begin. We'll take a look at vertical asymptotes. And you find the vertical asymptote by setting the denominator equal to 0, just like finding the zeros of a polynomial. For example, find the vertical asymptotes, and I have two examples here for you to be able to look at. The very first one, since it just says find the vertical, that's all we're going to look at. So we're going to look at the denominator, and we're going to set the denominator equal to 0 and solve for x, and I come up with x equals 2. This graph has a vertical asymptote at x equals 2, and that x equals 2 is a vertical line. Let's take a look at that on Desmos. Okay, now if you can see my graph, I have it colored blue. Okay, so this is the actual graph of x plus 7 over 2 minus x. I have graphed the asymptote x equals 2. In looking at it from this perspective, we can kind of see, okay, well, it looks like that line's going over there toward 2, and this line here, the curved line, is going over toward 2. But let's zoom out And the more we zoom out, we change our perspective, but we can look and we can see, okay, well, it's getting closer and closer to 2. The thing of it is even here it almost looks like it's turning purple, and down here it's turning purple. The thing of it is, I'll come up here and I'll go to 120. We'll see. Whenever we change our perspective and zoom in and get closer to that, you can kind of see there's now a gap, and the closer we zoom in, we'll see there is a gap. They never touch. All the way to positive infinity going up this way, and as I move down to the other portion of the graph, they never touch, and you can see it widening as I get closer and closer to the x-axis. But same here, once I go down here to this portion and I zoom in, I could keep zooming in all the way down to negative 999 million, and they will never touch. The asymptote that I drew illustrates that that is a boundary in the two portions of this rational function, the graph. Remember, hyperbola is that we will have that distinction there, that both of these will get very close to 2, but they will never touch 2. Okay, so let's take a look at the other example. Okay, for the next example, we have h of x equals 3 minus x over x squared plus 2x minus 24. Same premise. We're to find the vertical asymptotes, so we're going to set the denominator equal to 0. In order to do that, I turn around and I factor. I say x plus 6 times x minus 4. I end up with 2 values. I end up with x equals 6 and x equals 4. That means I have vertical lines in 2 different spots. There are 2 vertical asymptotes for this rational function. And again, let's use Desmos to be able to view that. Again, my function is in blue. The red lines are the asymptotes. They are not a part of that function. Again, both of these will come very close to touching, but they will never touch. Even though it looks, the more that I zoom in though, you can see there's still a gap. There's still a gap. Okay, so still a gap. Same over here. These two will never touch the value of x equals a negative 6 and x equals 4. So let's talk about the y behind that. The y behind that for this one is because if the value of 2 is placed in there for x, I get a 0 in the denominator. I cannot have a 0 in the denominator. We've already covered this whenever we did rational functions in a prior chapter. Same here. If I plug in a negative 6, I will cause this to become 0. Or if I plug in a 4, I will cause this to be 0. Again, I cannot have the value of 0 in my denominator. Dividing by 0 is not allowed. Therefore, that's why those values will be considered asymptotes, and my function will never touch those values. The graph will never cross a vertical asymptote. It'll get right up next to it as close as it possibly can get, but it will never touch a vertical asymptote. Okay guys, that is vertical asymptotes. Please continue to watch your publisher videos. Structure and critically think about your homework. Reason through. Please understand why these asymptotes, why the function will never touch them, and how these are like a boundary to where your graph will go right up to it but will never actually get there. And in the next video we'll talk about some other asymptotes. Good luck on your homework.